Okay, we're back to look at section 9.3. We are revisiting Taylor series. So you might wonder, why are we back to look at Taylor series at all? Well, we know how to find Taylor polynomials. We did that in section 9.1. So we're going to extend Taylor polynomials to produce power series called Taylor series. So we're basically putting the last two sections together. So here is our definition of a Taylor series or a Maclaurin series. A Maclaurin series is just a Taylor series centered at 0. So again, we have to have all the derivatives of all orders on our interval containing a point A, then our Taylor series. This looks just like our Taylor polynomial did back in section 9.1. F of A, F prime at A, x minus A, plus F double prime at A, over 2 factorial x minus a squared, and so on and so on and so on. Written in a series form, this is the sum k equals 0 to infinity of f kth derivative at a over k factorial x minus a to the k. So what we're going to look at in this section is adding a couple of things. We need to know when our power series, which our Taylor series is a power series, these are just fancy coefficients, when the thing converges, and not only when it converges, but when our power series actually has the same values as our function. So those are the things we're going to look at. So as it says, the second point is a bit subtle, and we're going to start by looking at a Taylor series for f at a point, but we're not going to say that that Taylor series that our function actually equals that Taylor series, but we'll figure out whether that happens or not a bit later. So we're actually going to do this by looking at example 3 in the book. So example 3 is called manipulating Maclaurin series. So they want us to find the Maclaurin series for e to the x. So that basically involves coming up here and expanding e to the x at 0, right? So we're doing e to the 0 plus the derivative of e to the x evaluated at 0, x minus 0, right, and so on and so on and so on. This was actually previously done in the book, so they take a little shortcut here. But it wouldn't be a difficult thing to do. If you think about it, e to the 0 is 1, and then the derivative of e to the x is just e to the x all the time. So you're basically just going to get 1 repeatedly for the derivative part. So really all that you get is 1, and then x over 1 factorial, x squared over 2 factorial, and so on, so that our series is the sum k equals 0 to infinity, x to the k over k factorial. Well, now we want to know what the interval of convergence is. This is not something we did with Taylor series before. Well, this is exactly the kind of thing that you use the ratio test on, because we have a k factorial there. So if you do the ratio test, and again we have to do this with absolute values in here, you do a little bit of simplifying, you're going to get left with an x and a k plus 1 on the bottom. If you think about k staying as a constant, then the limit as k goes to infinity of this thing is 0. So this works for all x, all the time. And so this thing converges on minus infinity to infinity. So if we could say that our Taylor series actually was our function everywhere, then we'd say that they're the same everywhere, because it converges everywhere. We're not ready to say that yet, but if we could, there we go. Okay, we're going to kind of skip this stuff on the binomial series, and we're going to go look at convergence of Taylor series. So let's just read this paragraph. It may seem that the story of Taylor series is over, but there is a technical point that's easily overlooked. We know how to write a Taylor series, and we know how to find its interval convergence. What we don't know is that the series actually converges to f. So that's what we need to do. So Theorem 9.1 gave us the tools to do that, and that is the remainder term. We looked a little bit at this remainder term back in 9.1, but not a lot. So basically our function is Pn of x plus Rn of x, for Pn is the nth order Taylor polynomial, and Rn is our remainder term. So we went out like 8 terms, and then there'd be a remainder term, and that is fx. So in order to have convergence, what we need to happen is we need this Rn of x term to basically disappear, so that the Taylor polynomial, Taylor series, when we let it go to infinity, equals fx, and this term just disappears. So that's what theorem 10.7 says, is that the Taylor series for f centered at a converges to f for all x in I, if and only if the limit as n goes to infinity of Rn of x equals 0 for all x in I, where Rn of x is fn plus 1 of c over n plus 1 factorial x minus a to the n plus 1, and c is some value between x and a. Okay, so we're going to take a look at doing this with our e to the x series that we're just looking at. So we want to show that our Maclaurin series for fx equals e to the x converges to f for everything in minus infinity to infinity. So we have our Maclaurin series that we had from example 3, and we know it converges on minus infinity to infinity. The remainder term, we're just plugging into here. So that's going to look like e to the c, because our derivative is e to the x, we're evaluating at c. E to the c over n plus 1 factorial x to the n plus 1. That's just directly plugging into here. A is 0 in this case. Remember, our c is a value between a and x. Well, here that puts it between 0 and x. So that puts us with e to the c is somewhere between e to the 0 and e to the x. Okay, sorry, I had a little dog barking incident there, so I had to stop. We were looking at this, and we know that e to the c is between e to the 0 and e to the 1. And we want to look at Rn of x and show that its limit goes to 0. Well, even a little more, like slightly better than that, we could show that the absolute value of Rn of x, if we take the limit of that, goes to 0. And if you think about taking the absolute value of this Rn of x term, well, e to the c is always between e to the 0 and e to the x. Well, that's going to put it definitely less than e to the absolute value of x, because e to the minus x is less than e to the x all the time. So we can actually set this up using the absolute values of the terms. So now we're looking at the limit as n goes to infinity of e to the absolute value of x over n plus 1 factorial, absolute value of x to the n plus 1. Well, e to the absolute value of x, once you fix x, is just a constant. And so you're looking at the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial. Well, n plus 1 factorial, by our growth rate chart, is like more powerful. It grows faster than x to the n, so this is 0. So these things actually converge. And they have a neat little illustration here, where as you increase the degree of the Taylor polynomial, see we're up to Taylor polynomial, it goes all the way up to 50. It's pretty much a perfect fit as far as we can tell on here for e to the x. It's not, but it looks like it on here. Let's continue and look at cosine x. Now, they give the Maclaurin series for cosine x. By the way, there's a table, 9.5, of some handy series here. And some of these were on that link that I gave you in class with all the power series. But there's a handy link here, and you could rederive these, right? But we're doing this for cosine. So there's the expansion for cosine. It turns out to be the sum, k equals 0 to infinity, of minus 1 to the k, x to the 2k over 2k factorial. And this converges to cosine from minus infinity to infinity. That's what we want to show. So we need to show that the limit of the remainder term goes to 0. So our remainder term is fn plus 1 of c over n plus 1 factorial to the x to the n plus 1, where c is between 0 and x. So here we want to look at what f, the nth plus 1 derivative of c, looks like Well, it's either plus or minus sine of c, depending on exactly what's going on, or plus or minus cosine of c. Well, any way that we look at it, those are all bounded and going to be less than 1. So a remainder term, which would be the absolute value of that, is going to be bounded by a 1 on the top there. So basically this is just going to be less than or equal to absolute value of xn plus 1 over n plus 1 factorial. Well, if you hold x fixed, again we have similar to the last time, n factorial goes faster than x to the n, so this goes to 0. So our power series converges to cosine of x for all x. And once again, they do a cool little approximation down here. Doing something like this would be a pretty neat exploration project, right? If you did maybe graph for me, you could do this kind of thing in Desmos, I think. I don't know if you can put the series in there and do it with a slider. You could probably do this in CoCalc or something. But you could set this kind of thing up by just showing me all the different Taylor polynomials up to a certain place. You can see as you increase, it just keeps matching more and more and more of the cosine curve. Okay, that's it. I'm going to give you a couple problems, but I'm going to stop right there.